Section 6.3 is titled Simplify Radical Expressions. Please recognize that from here on out we're going to assume that numbers under the radical represent non-negative numbers. What this means is when we simplify an expression that's got a variable in it, if it's got an even root, we are not going to worry about putting absolute value brackets around the simplified expression because we're assuming that there are non-negative numbers being placed in for those variables. We want to first learn how to simplify expressions. So the first problem that I'd like to do is the square root of 80. While I could take my calculator and find out the square root of 80, when we say simplify a radical expression, what we mean is to rewrite this as the product of two values, and I'm going to use 16 times 5. Those two numbers multiply together to be 80. I picked the 16 and the 5 because 16 is a perfect square. I could have used a 4 and a 20 because 4 times 20 is 80 and 4 is a perfect square. As a matter of fact, here's my list of perfect squares. The first one is the number 1 because 1 squared is 1. The next one is the number 4 because 2 squared is 4. The next one is 9. And the next one is 16 and 25 and 36 and 49 and 64 and 81 and 100, etc. Those are all called perfect squares. I wanted to write 80 as the product of two numbers. I picked 16 times 5 rather than 4 times 20 because 16 is the largest perfect square. And that allows me to simplify because the square root of 16 is 4. And then the square root of 5 I can do nothing with, and this expression is simplified. I'm all done. Had I written this as the square root of 20 times the square root of 4, then here I would have had a 2 times the square root of 20. Well, that's not simplified as this is, because the square root of 20 can be thought of as the square root of 4 times the square root of 5 as well. And the square root of 4 is 2, so what I have up front here is 2 times 2 times the square root of 5. And 2 times 2 is 4, and I get the same answer I got way back here. It just took me a lot more work to get there. So look to write this as a product of two values, where one is a perfect square, and use the largest one out of this list, and the list could keep going. I can simplify with cubes as well, but I just have to think of the list of perfect cubes. The list of perfect cubes is similar to this in that it's gotten the same way. The first perfect cube is a 1. And the next one is an 8. And the one after that is a 27. And the one after that is a 64. So I'm looking to write 108 as the product of two numbers where one of them is from this list. And I've discovered, using my calculator, that's the way you're going to find it, that 27 divides into 108 4 times. And so I can break this as a product of the cubed root of 27 times the cubed root of 4, and the cubed root of 27 is 3, because 3 times 3 times 3 gives me 27. And so my simplified form of the cubed root of 108 is 3 times the cubed root of 4. Let's go ahead and do another one at the same point here. Well, actually, I think I'll go ahead. This problem, square root of 175y to the 6th, again, I'd like you to think of it as two parts. Actually, I'll write it as 3 parts. The 175 is an important thing to me, and I'm going to look at this list and recognize that 25 divides into 175 7 times. So I have square root of 25 times the square root of 7. The square root of y to the 6th is kind of nice because I remember that I can write that as y to the 6th raised to the 1/2 power, or write y to the 6 over 2 power, or finally y to the 3rd. And so I'm going to simplify that in that way. So right here I'm going to take the square root of 25, that's a 5. I'm going to go ahead and write this so you can see what I'm getting at. The 6 over 2 is the fractional exponent for that, or y cubed. I don't wish to write that anymore if I can get away with it. And so what I have here is 5y cubed times the square root of 7. And I have simplified this expression. Okay, I want to simplify this expression, the square root of 75, p to the 3rd, q to the 4th. I'm going to break this down into several factors underneath one radical symbol instead of writing individual radical symbols for each factor. It means the same thing. for example, the 75, I'm going to write as 25 times 3. Now our book writes this as 5 times 5 times 3 and writes it in its prime form because the square root of 5 times the square root of 5 is 5. I prefer to go ahead and just write this as the square root of 25. You have to decide what you like better. And as a matter of fact, I'm maybe going to do this next piece a little bit differently than our book. P cubed, I'm going to write as p to the second power times p to the first power because those exponents add to be 3. The reason I do that is I'm going to write this with an exponent that's divisible by 2 because my index is 2. And I know that I'll be able to simplify that. The q to the fourth is already an exponent that is divisible by 2. So I'll be able to simplify that. In other words, I'll have 4 over the index of 2, or the square root of q to the fourth is q squared. So what I like to do is I like to check off these factors as I take care of them. The square root of 25 is 5. I've pulled it out from the radical, so I've used that. The square root of p squared is p. I have 2 over 2 as an exponent, or p to the first power. I've taken care of that. And the square root of q to the fourth power is q to the second power, because 4 over 2 is 2. Or I could say to myself, q squared times q squared is q to the fourth. And what I have left then is this 3p under the radical. I can't do anything with it. This is what I could pull out. That has to stay. This expression is simplified. I'd like to simplify this expression, the fourth root of what's under this radical, or called the radicand, the 162, c to the fourth, d to the sixth. I'm going to attempt to take a look at this problem the way our book does this. And so I'm going to break 162 into its prime factors. And I know that 2 goes into 162 81 times. And after that, I know 81 factors into 3 times 3 times 3 times 3. I'm going to help you visualize this whole process. I'm going to have you think of c to the fourth as c times c times c times c, and then d to the sixth as d times d times d times d times d times d. And what our book does a very fine job of helping you to understand, and so I'm doing this a little bit differently than I have the previous problem, is that if I have the fourth root of something that I have 4 factors of, in this case, I have the fourth root of 3 to the fourth power, then what I have is 3. I have the number 3. So I'm going to pull that out in front of the radical. And likewise, I have the fourth root of c to the fourth power. Well, what I have then, when I pull that out from under the radical, is c. And finally, the fourth root of, in this case, I'm going to look at 4 of those factors of d, will be, or fourth root of d to the fourth power is d. And finally, I'm left with, underneath the radical, the 2 and d to the second power. And I have simplified this expression. I may have done this problem a little bit differently had I thought of 162 as 81 times 2, because I know the fourth root of 81 is this 3. I might have left the c to the 4 there because I know that c to the fourth, and I want the fourth root of it, gives me c to the first. 4 divided by 4 is 1. And then I probably would have written d to the sixth power as d to the fourth times d to the second, because I know this expression right here, d to the fourth, when I take the fourth root of it, gives me d to the first. And I might have crossed this out and said that is equal to this 3, this is equal to this c, this is equal to this d, and I'm left with the 2d squared underneath. 2 ways to go about this way, writing in its prime factored form. In this way, writing in its factors form, where I chose to make these exponents divisible by 4 and make sure I used, in this case, I added those exponents, so I got this d to the sixth power. You have to decide how you like to work. I really prefer to show you the shortcut to this rather than writing these out in factored form. And so what I'm going to do, because I have an index of 5, I'm taking the fifth root, I'm going to write these bases, these factors, so that they are the product of 2, where one of them is divisible by 5, so I can simplify that factor individually. So I'm going to write the p to the 14th as p to the 10th times p to the 4th. Because those exponents add to be 14, and 10 is divisible by 5. Now I wanted to pick the largest number that's divisible by 5, this 10, rather than a 5. I could have used here, some people would say, why didn't you use a 5 and a 9? Well, I want to take the largest number divisible by 5 and have left here something that is less than 5. Q to the 9th, I'm going to write as q to the 5th times q to the 4th, because this 5 is divisible by its index, and I have left here, when I add these to be 9, I have left a number that's less than 9. The r to the 23rd, I'm going to put a 20 and a 3 as exponents, because they add to be 23, but this is also the largest exponent that's divisible by 5 that's not greater than 23. Now I'll go ahead and simplify, and so I'm going to take this p to the 10th first. 10 divided by 5 is 2, so I've simplified that because that would have been 10 p to the 10 fifths. Q to the 5th, the 5 divided by 5 is 1, so I'll have q to the 1st, taking care of that. The r to the 20th, 20 divided by 5 is 4. I'm going to put little multiplication symbols between there, and I've taken care of that. What is left underneath my radical is p to the 4th, q to the 4th, r to the 3rd. I'm sure of the fact that those are simplified because none of those are larger than 5, and I have the simplified expression. Here's two examples. I'm going to do them dramatically different. The product rule for radicals says that if I have the product of two radicals, I can multiply the values underneath and then simplify if possible. And that's what I want to do here, multiply and simplify. So in this first example, the square root of 2 times the square root of 32 is equal to the square root of 64 because I chose to multiply 2 times 32. And I did that because I knew I was going to get a 64, and I knew that the square root of 64 is equal to 8. Simple problem. But I have large numbers here. So you might choose to, and it's up to you how you're gonna work with this. You might choose to write these in their prime factored form and then find, since I'm looking for a square root, pairs of factors to be simplified. So the number 24 can be written as 2 times 2 times 2 times 3. That's the prime factorization of 24. The number 75 can be written as 3 times 5 times 5. And in doing this problem this way, what I'm going to do now is look for pairs of factors so that I can simplify them, like this pair right here. The square root of 2 times the square root of 2 is 2. Again, remember, the square root, underneath the radical, that would be the square root of 4, and the square root of 4 is 2. So I've got a factor of 2 out in front. And then I've got this pairing of 5s. Square root of 5 times the square root of 5 is 5. And then don't lose this. These are just factors. They're just under different radicals, but I can say that that's the square root of 3 times the square root of 3, which is just 3. And finally, what I have left, and I can do nothing with under this radical, is this lone 2. And I will multiply these factors out. 2 times 5 is 10, and 10 times 3 is 30. So I have 30 times the square root of 2. That's probably the best way to do this problem. The other possibility, I'm going to go ahead and show this to you. Here, there's my answer. The other possibility, and this might be what I might have thought of doing, is to break each of these into their factored form and think of square root of 24 as 4 times 6, and think of 75 as 25 times 3. And then go ahead and pull out 2 for that factor, pull out 5 for that factor. So I've taken care of this one and this one. And what I have left then is 6 times 3 under the radical, or the square root of 18, which is 10 times the square root of 18. But I all of a sudden noticed that the square root of 18 can be broken into the square root of 9 times the square root of 2. And this is equivalent right here to a 3. And so you have 10 times 3, or 30, times the square root of 2. And I got the same answer as before, not breaking them into their primes, but breaking them into factors and noticing that there were some perfect squares, and then at the end saying, oops, I got to get another perfect square out of there, and then finally simplifying this problem. Again, you decide. Multiply and simplify. I'm going to go ahead and do this problem by breaking this out into its prime factorization. Possibly an easier way to do this problem, I would have to say. And I'm going to put the numerical factors in front. So I'm going to write these all together. So this 2 times this 12 and I'm going to write 12 as 2 times 2 times 3. So here's the 2, and here's the 12, right there. Then this x cubed and this x to the first power, I'm going to notice that that is 4 x's. Or I could have written there x to the 4th. And y times y, I'll go ahead and write as y times y at the end there. And now I'll go ahead and simplify. Again, I'm taking the square root. So this right here, that pairing, will be equal to 2. Interesting, careful, look at this pairing and this pairing. Each of those, the square root of those, is x. And so what I had x to the 4th, I was taking the square root of that. That gives me x to the 2nd power. This individually gives me x times that x gives me x squared. And then this pairing right here, the square root of y times y is y. And finally, under the radical, I'm left with the 2 times the 3, or the 6. Now, had I not done this problem this way, had I just gone ahead and taken 2 times 12 and gotten a 24, and then x cubed times x to the 1st is x to the 4th, and y times y is y squared, I could have just seen a little bit, maybe more quickly than to write this in its prime form, that I would have written the square root of 24 as 4 times 6. I'm not going to worry about the x to the 4th or the y to the 2nd because I know that they can be simplified because they are even and divisible by 2. The square root of 4 here is 2. Taking care of that. The square root of x to the 4th is x to the 2nd power. Taking care of that. The square root of y to the 2nd is y. And then I have this 6 underneath the radical, and I'm all done. Again, write it in its prime factored form, or go ahead and multiply these together and get this expression and simplify from there. I'm absolutely going to go ahead, since I'm taking the cube root of each of these, multiply what's under the radicals first. So s to the 2nd power times s to the 4th power is s to the 6th because I add their exponents. T to the 4th times t to the 6th is t to the 10th. Again, because I add their exponents. And my goal now is, because I know the property with fractional exponents and radicals, my goal is to make each of these, break them apart so that they are factors that have exponents that are divisible by the 3. So the s to the 6th, I don't need to do anything with. But the t to the 10th, I'm going to think of as t to the 9th times t to the 1st. Those exponents add to be 10, and this 9 is divisible by 3. Remember that property that says this cubed root of s to the 6th is the same thing as s to the 6 over 3 power. And the cubed root of t to the 9th is the same thing as t to the 9 over 3 power. Again, I'm showing you something that I've been doing without writing the last few problems. This right here reduces to s squared. This right here reduces to t cubed. And underneath the radical, I still have a t to the 1st, the cubed root of it. Again, I will not write this step typically. I wanted to just remind you of it. I better put this here so it's not confusing. 6 divided by 3 is my 2. 9 divided by 3 is my 3. I pull them out from under the radical. The t to the 1st power cannot be evenly divisible by 3. I leave it underneath the radical. This expression is multiplied and simplified. We've been multiplying expressions that have the same indice or the same root. The square root of something times the square root of something, or the cubed root of something times the cubed root of something. But now what I'd like to attack is a problem where we take the cubed root of something times the 4th root of something. When these indices are not alike, it is not proper for me to go ahead and multiply the 5 times 2 and get a 10. I can only do that when the indices match. So the only way to go about multiplying this problem is to write these as fractional exponents. So the cubed root of 5, I'm going to write as 5 to the 1/3 power. And the 4th root of 2, I'm going to write as 2 to the 1/4 power. And I believe that the only way I can simplify this is to get common denominators, even though their bases aren't alike, and then I'll write it with using the properties of exponents. So I see that a common denominator here is a 12. So I will have 5 to the 4/12 and 2 to the 3/12 power. And so ultimately it looks like I'm going to write this expression and raise it to the 1/12 power because these have common denominators of 12. Well, if I do that, the 5 has to be raised to the 4th, its numerator, and the 2 has to be raised to the 3rd, its numerator. Again, properties of exponents say multiply these. 4 times a 12th is 4 twelfths. 3 times 1 12th is 3 twelfths. So what I ultimately have here is the 12th root of 5 to the 4th times 2 to the 3rd. I could leave it at that. It happens that 5 to the 4th is 625. And 2 to the 3rd is 8. And that is equal to 5,000. And I have to use my calculator or I'd scratch it out, is what I do. But we have multiplied and ultimately simplified this expression. Again, the only way to multiply this expression, given that their indices are different, is to write them with fractional exponents. So I will have here a to the 3/4 power times a to the 2/3 power. This one's kind of nice because their bases are alike. But before I go any further, I need to get common denominators of 12. So I'm going to write this first factor. Let's see, a to the 9/12 power. It's the same thing as 3/4. And the second factor as a to the 8/12 power. And now, because their bases are alike in this particular problem, I get to add their exponents. And 9 and 8 is 17 twelfths. So what I'm asking for here is the 12th root of a to the 17th power. I really shouldn't stop here because I have a number that's bigger than 12 here, so this can be simplified. And what I will do to do that is I will write a to the 17th as the product of two factors, those factors being a to the 12th times a to the 5th, because that adds to be 17, and I chose those because I needed one of these in order to simplify it to be divisible by 12. This 12th root of a to the 12th power is a, because 12/12 is 1, and then I'm left with a to the 5th as a radicand and the 12th root of that. And I have both multiplied and simplified. Here's a challenging problem. The 4th root and square root of the two expressions under the radicals. Of course, I will take this 9a, b to the 3rd power, and raise it to the 1/4 power. And the 3, a to the 4th, b, I'll raise that to the 1/2 power because I'm taking the square root. I can raise all of this to their respective powers, and I will do that. I believe, though, that before I do that, what I'm going to do is I'm going to write these so that they have common denominators. So I'm going to think of 1/2 as 2/4. And so what I will have then here is a 9 to the 1/4 power, an a to the 1/4 power, a b to the 3/4 power, etc. I also think that before I even do that, I'm going to think of this 9 here as 3 to the 2nd power. I'm trying to decide if I want to take the space to do that. Again, think of this as 3 to the 2nd power. So 3 to the 2nd power raised to the 1/4 power will be a 2/4 as an exponent. I will have a to the 1/4 and b to the 3/4. Again, I'm multiplying the exponents. Here I will have 3 to the 2/4. Again, I'm raising these to this power. This a to the 4th multiplied by 2/4 is going to give me a to the 2nd power, because I'm reducing the 4's, and I will have b to the 2/4 power. And now I have many factors that are being multiplied together, and I can add their exponents when their bases are alike. So this base of 3 raised to the 2/4 power in each case, I'm going to add the exponents. 2/4 plus 2/4 is 4/4, or 3 to the 1st power. A to the 1/4 and a to the 2nd power, I'm going to go ahead and call that a to the 9/4 power. That is 2 1/4. And b to the 3/4 and b to the 2/4 power is b to the 5/4. And now I'm ready to rewrite this with 4 as my radicand, but however the 3 is going to stay outside because I don't need to complicate things. It is the number 3. So I have the 4th root of a to the 9th and the fourth root of b to the fifth. That's what this expression represents. Next, and maybe you don't even need to write this step anymore, I'm going to write a to the ninth as a to the eighth times a to the first. Those add to be 9. The 8 is divisible by 4. I'm going to write b to the fifth as b to the fourth times b to the first. Same reasoning. And finally, a to the eighth, but I want the fourth root of that. 8 divided by 4 is 2. So I have an a squared. B to the fourth, and I want the fourth root of that, is b. So I've taken care of this and this. And underneath the radical, I still have an a, b. And remember, it's to the fourth root of. Objective B in section 3, the directions are to divide and simplify. A little bit simpler than some of the multiplication problems we were looking at. I've got two radicals that I want to divide, and like when I multiply, and I can put all the factors under one radical, and vice versa, break it apart. When I divide, I can take this expression and put it under a single radical, and look at this as the square root of 30x divided by 10x, one radical involved. And the reason I would do this is because the x's are equal to 1, and I would reduce those, and 10 goes into here once, and 10 goes into here 3 times, and what I'm left with is the square root of 3. That's it. It's that simple. Let's look at another problem. If I have the square root of 52ab cubed divided by the square root of 13a, I can put them under a single individual radical and go ahead and reduce if it's possible. And so the first thing I see is those a's. Those are equal to 1. But I believe 13 goes into 52 4 times. And as a result, what I'll have here is the square root of 4b cubed. Be careful, you're not done. The square root of 4b cubed, again, I'm going to write it the way I have been. And that is, I'm going to write b cubed as b to the second times b to the first. Because the square root of 4, for example, I can reduce. That's 2. The square root of b squared is b. It comes out from underneath the radical. And what I'm left with is the square root of b underneath. In this problem, be careful. We're dividing and simplifying, but this 2 is just a 2 in the denominator. Matter of fact, if I wanted to pull that away from this, it is a 1 over 2, or the fraction 1/2. And I might do it just like that. I think I'll write that as 1/2. And then I'm going to look at what's under the radical, the 48ab and the 3 together now so that I can reduce that. Because I know that 3 goes into 48, and it goes into there 16 times, and what I have then is 1/2 times the square root of 16ab. Now I won't go and break this apart any further, just recognize that you have the square root of 16 here. Well, that's 4. These can't be reduced because they don't have an exponent that's evenly divisible by 2. So I have 1/2 times 4, the square root of 16, times the square root of ab. And this, of course, can be reduced, and so I'm left with a factor of 2 in front times that square root of ab, and I've reduced this expression. Again, here's where it gets a little bit tricky. I'm asking you to divide, but the indices are not the same. The numerator is the square root of x. The denominator is the fourth root of x. Every time that this has happened, we've had to put this, rewrite these with fractional exponents. So the square root of x needs to be written as x to the 1/2 power. And the fourth root of x needs to be written as x to the 1/4 power. And now, all I need to do is I need to subtract. But in that process of subtracting, I need to remember to change that 1/2 to 2/4 so that I can subtract those exponents. And 2/4 minus 1/4 is 1/4. And finally, we would write this expression as the fourth root of x, putting it back in radical form. Again, rewriting with fractional exponents, I'm going to write this as a to the fourth, b to the second, raised to the 1/5 power, and then a b squared raised to the 1/3 power. I'll go ahead and change these exponents to have a common denominator of 15 before I take this any further. Please recognize that 1/5 is the same as 3/15 and 1/3 is the same as 5/15. So I'm now going to go ahead and take these exponents and multiply them by 3/15 and in the denominator by 5/15. So a to the 4th raised to the 3/15 power is a to the 12 over 15. B to the 2nd raised to the 3/5 power is b to the 6 over 15. In the denominator, a to the 1st raised to the 5/15 power gives me a to the 5/15. B to the 2nd raised to the 5/15 power, multiply again, is 10/15. I'm now ready to go ahead and subtract because these bases are alike, and subtract right here again because the bases are alike. 12/15 minus 5/15 is 7/15. And here 6/15 minus 10/15 is a minus 4 over 15. Recognize that this factor, b to the minus 4 over 15, needs to be moved downstairs into the denominator. So I'm going to write that, I'm looking for space here, I'm going to write that a to the 7/15 will stay where it is, and b to the 4/15 will go downstairs. And now I'm going to say, well, common denominators in those fractions, so I'm going to raise all of this to the 1/15 power, and I will have a to the 7th over b to the 4th. And finally, I should take the last step and state that I'm looking for the 15th root of, right here, a to the 7th divided by b to the 4th. I have divided, having to put this in terms of fractional exponents, subtracting where the bases were alike, getting rid of this negative exponent, moving it downstairs, and rewriting it in radical form so that it uses the same indice under one expression. Sometimes when you're asked to divide and simplify, an expression like this has nothing that can be simplified underneath the radical symbol. So what you might like to do is to think about each of the factors and or quotients individually. This 32, I want to take the 5th root of it. I'm going to write these separately so you can just see and think about each factor individually. The reason I did this is I knew a couple of things. There is no prime number or no factor that divides into the numerator and the denominator evenly. It happens that this is only divisible by 2. Those are the prime factors. There are 5 2's in the number 32. And this is only divisible by 3. So I chose not, and I can't do anything with those. So let's look at these each separately. The 5th root of 32 is equal to 2 because 2 times 2 times 2 times 2 times 2, 5 times, gives you that 32. Again, back to this rewriting a radical expression as a fractional exponent. Remember that this could be written as b to the 10 divided by 5 power, or it simplifies to be b squared. The 5th root of 243 is equal to 3 for the same reason as up above. 5 factors of 3 give you 243. And then this simplifies right here. Again, remember, as a fractional exponent, 20 divided by 5 is 4. And we're all done simplifying that problem. There was nothing we could do in the beginning to simplify it, so I decided to share and show you to think of those each individually and simplify those like that. This is the last problem I'd like to do in section 3. Again, a division, divide, and simplify problem. But the bases in this problem are not alike, so there's nothing we can do to simplify underneath the radical. I'm going to, for one last time, just to kind of firm up this process, break this p to the 9th into 2 factors, where one of them has an exponent that's divisible by 6. The others are already divisible by 6. So the p to the 9th I'm going to write as p to the 6th times p to the 3rd. Again, those exponents add to be 9, and this factor right here has an exponent that's divisible by 6. q to the 24th, the exponent is already divisible by 6, and r to the 18th, that's true as well. So finally, the 6th root of p to the 6th power is p. and I've taken care of that factor. The sixth root of q to the 24th power, the 24 divided by 6 is 4, so I have q to the 4th power. And then downstairs, the sixth root of r to the 18th power is r to the 3rd, because 18 divided by 6 is 3. I'm sorry, I should have been marking those off. So those have all been taken care of. It is just the sixth root of p to the 3rd that could not be simplified, and it had to stay under the radical. Again, this is the last example for this section. We'll move on to section 4.